And now in this lecture we'll answer two questions. In the first question we'll find out the area of this circle, and in the second question we'll find out the area of this trapezoid ABCD. We start with the first question. So in the drawing we have a circle, and we have also this common standpoint, point P. From this common standpoint, point P, we have two tangents to this circle, tangent PA and tangent PB. In addition, we have the right triangle ACP. The right triangle ACP cuts the circle at 2 points, point A and this point. This is the right angle ACP is the right angle, and side CP of the right triangle ACP is equal to 4 units in its length. Line 7 BC is equal to 1 unit. Again, our mission is to find out the area of this circle. So here we can implement rule 2. Repeat quickly rule 2. According to rule 2, the lengths of two tangents from a common standpoint to a circle are equal. So in the drawing we have a circle, and this is the common standpoint, point P. From this common standpoint, point P, we have two tangents to this circle, tangent PA and tangent PB, and according to this rule 2, they are equal to each other. That is to say, PA equals to PB. So we can actually implement rule 2 in our drawing. Why? Because in our drawing, we have this is the common standpoint, point P. From this common standpoint, point P, we have two tangents to this circle. From this common standpoint, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to rule 2, they are equal to each other. This is to say, PA equals to PB. So I write it down. The length of tangent PA is equal to the length of tangent PB according to rule 2. But it is given as the question that the length of this common standpoint, the length of tangent PB, the length of this tangent PB is equal to 4 plus 1, that is 5. PB equals to 5. So if you write here that PB equals to 5. And from this equation, PA equals to PB equals to 5, we will derive that PA is also equal to 5 units in its length. So here PA equals to 5. PA equals to 5. In the next step, I'll copy the right triangle ACP in a new page, and we will implement the Pythagoras theorem on this right triangle ACP. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse is equal to the sum of the sides of the perpendiculars. Here by PT is a version for Pythagoras theorem. So actually, this is the right triangle ACP that I quote from the original drawing. According to the Pythagoras theorem, in this right triangle ACP, AP squared, that is the square of the hypotenuse, is equal to AC squared plus CP squared. So I write it down. AP squared, that is the square of the hypotenuse, is equal to AC squared plus CP squared. The hypotenuse AP is 5, therefore the square of the hypotenuse is 5 squared, that is 25, and it is equal to AC squared. AC is the missing side, so we know it is so AC squared plus CP squared. CP is 4, therefore CP squared is 4 squared, that is 16. So in total, if we found out that 25 equals to AC squared plus 16. Here we subtract 16 from this equation, and we get that AC squared is equal to 25 from 16 is 9. So AC squared equals to 9. Here we take a root out of this equation, and finally we get that the missing side AC is equal to the square root of 9, that is 3. So AC equals to 3 instead. This is the missing side AC, that is equals to 3 instead. So AC equals to 3. In the next step, we define the center of this circle. This point is point O. And we will also define the radius of this circle as x. In the next step, we will join points O and B together by a straight line. Point O is the center of the circle, point B is the point on the circle itself, therefore OB is the radius of this circle, that is equal to x according to our definition. So here we can implement rule 1. I'll repeat quickly on rule 1. According to rule 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. So in the drawing we have a circle, and we have the tangent AB. This is tangent AB, that is tangent to this circle, that is point M. Point M is the point of tendency of tangent AB with this circle. In addition, we have the radius OM that is equals to R, so the radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule, rule 1. So we can actually implement rule 1 in our drawing. Why? Because we have the radius OB that is equals to x. The radius OB is drawn to point B, that is the point of tendency of tangent PB with this circle. And whenever you have a radius that is drawn to the point of tendency, then PB will be perpendicular to the radius BO. If PB is perpendicular to BO, it means that this angle is equal to 90 degrees. It is the right angle. It is given us the question that PB is a tangent to the circle at point B. So PB is a tangent, it is absolutely a straight line. So if we focus on the upper side of this straight line PB at point C, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of PB at point C? We have this angle that is right angle plus this missing angle. In total must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. According to rule 3, of course. In the next step, from the center of this circle, that is to say from this point O, we will draw perpendicular on AC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the turning point of the perpendicular from point O, and AC this point is point E. By doing this construction, we created quadrilateral OECB. Inside quadrilateral OECB, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total it must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So, inside quadrilateral OECB, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we know that quadrilateral OECB is a rectangle because it has 4 right angles. So write it down. Quadrilateral OEBC is a rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So a rectangle OECB, side OE must be equal to the opposite side CB, but CB is 1, therefore OE must be also equal to 1. Likewise, according to the sum rule, in the same rectangle OECB, side OB must be equal to the opposite side EC, but OB is x, therefore EC must be also equal to x. What is the length of this line segment AE? On the drawing it is very easy to see that AE in total equals to AC minus CC. Again, AC minus CC equals to AE. So I write it down. AE equals to AC minus CC. So AE equals to AC. AC is 3 minus EC. EC is x. So in total, AE equals to 3 minus x units in its length. A equals to 3 minus x. In the next step, we join points O and A together by a straight line. OA is the radius of this circle, that is equal to x. In the next step, I'll copy the right triangle OAE in the new page and we'll implement the Pythagoras theorem on this right triangle, triangle OAE. This right triangle, triangle OAE. Side A equals to 3 minus x units in its length. Side O equals to 1 unit in its length. And the hypotenuse OE equals to x. Here by PT is the promotion for Pythagoras theorem. Carefully, this is the right green triangle, triangle OAE that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle OAE, OA squared, that is the square of the hypotenuse, is equal to AE squared plus OE squared. So I write it down. OA squared, that is the square of the hypotenuse, is equal to OE squared plus AE squared. OA is x, therefore OA squared is x squared, and it is equals to OE squared. OE is 1, therefore OE squared is 1 squared, that is 1. plus AE squared. AE is 3 minus x, therefore AE squared is 3 minus x squared. So in total we should find out that x squared equals to 1 plus 3 minus x squared. Here we'll open the brackets on this side of the equation and finally get that x squared equals to 1 plus 3 minus x squared. 3 minus x squared equals to 3 squared, that is 9, plus x squared, minus 2 times 3 times x, that is minus 6x. Here we have x squared on both sides of the equation, so x squared will get cancelled. After cancelled x squared, this side of the equation we are left with nothing, that is to say 0. On the other side of the equation, we have 1 plus 9, that is 10, minus 6x. So total we should find out that 0 equals to 10 minus 6x. Here we add 6x to this equation, and finally get that 6x equals to 10. Here we divide this equation by 2, and finally we get that 6x over 2 is 3x, equals to 10 over 2 is 5, so 3x equals to 5. Here we divide this equation by 3, and finally we get that x equals to 5 over 3 units in its length. So if we found out that the radius x of this circle is equal to 5 over 3 units in its length. Our mission is to find out the area of this circle. Actually, the area of any circle equals to pi times the radius of the circle squared. I'll write it down. The area of any circle is equals to pi times the radius of the circle squared. Therefore, the area of our circle will be equal to pi times the radius of our circle squared. The radius of our circle is x, therefore the radius squared is x squared. So in total we should find out that the radius that we are looking for, the radius of our circle, is equal to pi times x squared. We just write down found out that x equals to 5 over 3. If x equals to 5 over 3, it means that x squared is equal to 5 over 3 squared. So in total we should find out that the area of our circle is equal to pi times 5 over 3 squared. It's actually pi times 5 over 3 squared. 5 over 3 squared equals to 5 squared, that is 25, over 3 squared, that is 9. So in total we should find out that the area of this circle is equal to either 25 pi over 9 square units, so in terms of numbers, the area of this circle is equal to 8.727 square units. 8.727 square units. Repeat again, found out actually that the area of this circle is equal to either 25 pi over 9 square units, so in terms of numbers, the area of this circle is equal to 8.727 square units. So we finished with the first question. In the next step, I'll present to you the second question and we will solve it. Our mission in this second question is to find out the area of this trapezoid ABCD. It is given us the question that side AB of this trapezoid ABCD is equal to 16 units in its length, side BC equals to 25, AD equals to 17, and DC equals to 44. Again, our mission is to find out the area of this trapezoid ABCD. Actually, the area of any trapezoid is equal to the sum of its two parallel bases times the height over 2. In our trapezoid ABCD, the two parallel bases are AB and DC. And therefore, the area of this trapezoid ABCD will be equal to the sum of its two parallel bases, that is actually AB plus DC times the height, that is h over 2. So I write it down. The area of trapezoid ABCD is equal to the sum of its two parallel bases, that is actually AB plus BC times the height, that is h, divided by 2. The height h must create 90 degrees with two bases AB and DC. So do now we can find out that the area of trapezoid ABCD equals to the sum of its two parallel bases, that is actually AB plus DC times the height that is edge over 2. Repeat again, the height edge must create 90 degrees with the two bases, with the two parallel bases AB and DC. In order to find out the area of this trapezoid ABCD, we will do a construction. That is to say, from this point A, we will draw perpendicular on DC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to our construction. We define the touching point of the perpendicular from point. We define the touching point of the perpendicular from point A in DC. This point is point E. We define the length of line 7DE is X. We define the length of line 7AE is H. H is the height to the base, is the height of trapezoid ABCD. Why H is the height of trapezoid ABCD? Because H creates 90 degrees with the base DC of trapezoid ABCD. Therefore, the height edge of trapezoid ABCD, the height of trapezoid ABCD is H, that is AE. So in the next step, I'll copy the right triangle AED in the new page and implement the Pythagoras theorem on this right triangle, triangle AED. Here by PT is a version for Pythagoras theorem. So actually, this is the right triangle AED that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle AED, AD squared, that is the square of the hypotenuse, is equal to AE squared plus DE squared. So I write it down. This will be equation 1. AD squared, that is the square of the hypotenuse, is equal to AE squared plus DE squared. The hypotenuse AD is 17, therefore AD squared is 17 squared, that is 289. And it is equal to AE squared. AE is H, therefore AE squared is H squared plus DE squared. DE is X, therefore DE squared is X squared. So in total, we found out that according to equation 1, H squared plus X squared equals to 289. In the next step, we will do another construction. That is to say, from this point B, we will draw perpendicular on DC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the tangent point of the perpendicular from point B and DC. This point is point F. We know that side AB is parallel to side DC. Those two angles, they are both located between the parallel lines AB and DC, and therefore they are defined as an interior angles. In addition, those two angles, they are both located on the right side of H. Or they are both located on the right side of side AE that is equals to X. And therefore, for that reason, they are both defined as one-sided. So in total, those two angles, they are both defined as one-sided interior angles. And according to Rule 16, the sum of two one-sided interior angles is equal to 180 degrees. So I can click on Rule 16. According to Rule 16, the sum of one-sided interior angles is equal to 180 degrees. So those two angles 4 and 5, they are both defined as one-sided interior angles, and therefore the sum of them according to this rule, Rule 16, is equal to 180 degrees. Here, angle 4 plus angle 5 is equal to 180 degrees according to this rule, Rule 16. Likewise, those two angles that are 3 and 6, they are both defined as one-sided interior angles, and therefore the sum of them according to this rule, Rule 16, is equal to 180 degrees. Okay? Angle 3 plus angle 6 is equal to 180 degrees according to this rule, Rule 16. So we can actually implement Rule 16 in our drawing. Why? Because in our drawing, we have those two angles, they are both defined as one-sided interior angles, and therefore the sum of them is equal to 180 degrees according to Rule 16. So I write it down. This is a right angle, and the missing angle, this is the missing angle BAE. So actually, according to Rule 16, 90 degrees plus the missing angle BAE, in total the sum of those two angles are equal to 180 degrees according to Rule 16. So 90 degrees plus the missing angle BAE in total must be equal to 180 degrees. Here we subtract 90 degrees from this equation, and finally we get that the missing angle BAE is equal to 180 degrees minus 90 degrees is 90 degrees. Okay. This is the missing angle BAE that is equal to 90 degrees in its size. Likewise, we have those two angles that are both located between the parallel lines AB and DC, therefore they are defined as interior angles. In addition, those two angles, they are both located on the left side of the straight line BF, and therefore they are also defined as one-sided. So in total, those two angles, they are both defined as one-sided interior angles, And according to rule 16, the sum of two one-sided triangles is equal to 180 degrees. That is to say, this is the missing angle ABF plus the missing angle plus this is the right angle, this right angle. In total, it must be equal to 180 degrees according to rule 16. So I write it down. The missing angle, that is angle ABF, this is the missing angle ABF, plus this right angle, in total it must be equal to 180 degrees according to rule 16. And again, the missing angle ABF plus the other angle, that is the right angle, in total it must be equal to 180 degrees because of the fact that they are both defined as one-sided triangles, and according to rule 16, the sum of two one-sided triangles is equal to 180 degrees. So here we subtract 90 degrees from this equation, and we get that the missing angle ABF is equal to 180 degrees minus 90 degrees is 90 degrees. So if we found out in total that this is the missing angle ABF, that is the right angle according to rule 16. So if we found out that inside quadrilateral ABFE we have four right angles. And according to rule 5, any quadrilateral that has four right angles must be at least a rectangle if not a square. So in relation to quadrilateral ABFE, it's a rectangle because it has four right angles. Now write it down. This is quadrilateral ABFE, that is a rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ABFE, side AB must be equal to the opposite side FE. But AB is 16, therefore FE must be also equal to 16 units in its length. Likewise, according to the same rule, in the same rectangle ABFE, side AE must be equal to the opposite side BF. But AE is 8, therefore BF must be also equal to H. What is the length of line segment FC? From the drawings, it's very easy to see that FC in total equals to DC minus DE minus EF. Again, FC in total equals to DC minus DE minus EF. So I write it down. The length of line segment FC in total it equals to DC minus DE minus EF. So FC equals to DC. DC is 44 minus DE. DE is X minus EF. EF is 16. So in total, FC equals to 44 minus X minus 16. So FC equals to 44 minus 16 is 28. So in total, this expression is equal to 28 minus X. So we found out that FC equals to 28 minus X units in its length. In the next step, I'll copy the right triangle BFC in the new page and we'll implement the Pythagoras theorem in this right triangle, triangle BFC. Here by PT is the abbreviation for Pythagoras theorem. So actually this is the right triangle BFC that the current solenoid drawing. According to the Pythagoras theorem, in this right triangle BFC, BC squared, that is the square of the hypotenuse, must be equal to BF squared plus FC squared. So write it down. This will be equation 2. BC squared, that is the square of the hypotenuse, is equals to BF squared plus FC squared. The hypotenuse BC is 25, therefore BC squared is 25 squared, that is 625, and it is equals to BF squared. BF is 8, therefore BF squared is 8 squared plus FC squared. FC is 28 minus x, therefore FC squared is 28 minus x squared. So in total we found out that according to equation 2, 625 equals to 8 squared plus 28 minus x squared. Here we subtract 625 from this equation, equation 2, and finally get that according to this equation, equation 2, this side of the equation we left with nothing, that is to say 0. On the other side of the equation we have 28 8 squared plus 28 minus x squared. So in total, according to equation 2, we found out that 0 equals to 8 squared plus 28 minus x squared. Here we open the brackets on this side of this equation, equation 2, and finally we get that according to equation 2, we have 0 equals to 8 squared plus 28 minus x squared. 28 minus x squared equals to 28 squared, that is 874, plus x squared minus 2 times 28 times x is, that is minus 56x. So according to equation 2, I should found out that 0 equals to 8 squared plus 874 plus x squared minus 56x. Here we add 56x to this equation, equation 2. So 0 plus 56x is 56x. And it is equals to 8 squared plus x squared actually here we subtracted 625 from this equation, and 874 or 625 is 159. Again, 874 or 625 is 159. So in total we can find out that 56x equals to 8 squared plus x squared plus 159. According to equation 2, according to equation 1, we have already found out that 8 squared plus x squared equals to 289. So you can substitute 8 squared plus x squared in this equation, equation 2, by 289. We'll do it now, and we'll get that 56x equals to 8 squared plus x squared according to equation 1 is 289 plus 159. So 56x is equal to 289 plus 159 is 448. So here we divide this equation 2 by 56. And finally we get that according to this equation 2, x equals to 448 over 56. 448 over 56 is equal to 8. So x equals to 8 units in its length. According to equation 1, x squared plus x squared equals to 289. X equals to 8. If x equals to 8, it means that x squared equals to 8 squared, it is 64. Therefore, we can substitute x squared in this equation 1 by 64. We do it now and we get that according to this equation 1, 8 squared plus x squared, that is 64, is equal to 289. Here we subtract 64 from this equation 1. And finally we get that according to this equation 1, 8 squared equals to 289 minus 64, that is 225. Here we take a root out of this equation and finally get that h is equal to the square root of 225, that is 15. So x equals to 15 units in its length. So we found out that the height h of this trapezoid ABCD is equal to 15 units in its length. Our mission is to find out the area of this trapezoid ABCD. We have already found out that the area of trapezoid ABCD is equal to the sum of its two parallel bases, that is actually AB plus DC, times the height, that is h, divided by 2. AB is 16, DC is 44, the height h is 15, divided by 2. So in total, the area of trapezoid ABCD, that is the area that we are looking for in this question, is equals to 16 plus 44 is 60, times 15 divided by 2. 60 over 2 is 30, so in total this expression equals to 30 times 15, that is 450 square units. Okay, again, actually found out that the area of this trapezoid ABCD is equal to 450 square units. In the next step, we'll summarize the lecture. We start with the first question, of course. The first question, our mission is to find out the area of this circle. So in the domain we have a circle, and this is the common standpoint point P. From this common standpoint point P, we have two tangents to this circle, tangent PA and tangent PB. In addition, we have the right angle ACP. The right angle ACP cuts the circle at 2 points, point A in this point, and also at this point. And this is angle ACP, this is the right angle. Side CP of the right angle ACP is equal to 4 units in its length, and DC is equal to 1 unit. Again, our mission is to find out the area of this circle. So here we can implement all two, because we have the common standpoint point A, point P. From this common standpoint point P, we have two tangents to this circle, tangent PA and tangent PB. And according to all two, they are equal to each other. That is to say, PA equals to PB according to all two. And again, according to all two, PA equals to PB. But according to what is given as the question, the length of tangent PB in total is equal to 4 plus 1, that is 5. So we can write here that PB equals to 5, and from this equation PA equals to PB equals to 5, we derive that PA is also equals to 5. Here PA equals to 5. In the next step, I copy the right triangle ACP in a new page and implemented the Pythagoras theorem. This right triangle ACP. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse is equal to the sum of the squares of the perpendiculars. This is the right triangle ACP. This is the common from the original drawing. According to the Pythagoras theorem, in this right triangle ACP, AP squared, that is the square of the hypotenuse, is equal to AC squared plus CP squared. AP is 5, therefore AP squared is 5 squared, that is 25. And it is equal to AC squared. AC is the missing side, so we leave it as it is. So it is AC squared plus CP squared. CP is 4, therefore CP squared is 4 squared, that is 16. So in total we should find out the 25 plus 2 AC squared plus 16. Here we subtract the 16 from this equation and find out that AC squared is equal to 25 minus 16, that is 9. So AC squared equals to 9. We took out of this equation and found out that the missing side AC is equal to the square root of 9, that is 3. So AC equals to 3 instead 9. This is side AC is equal to 3 instead. In the next step, we define the center of this circle. This point is point O, and we define the radius of this circle as x. In the next step, we join points O and B together by a straight line. OB is the radius of the circle, and is equal to x according to our definition. Here we can implement rule 1 because we have the radius of B, that is 1 to point B, that is the point of tendency of tangent PB with this circle. And whenever you have a radius that is 1 to the point of tendency, then tangent PB will be perpendicular to the radius BO. If PB is perpendicular to BO, it means that this angle equals to 90 degrees according to rule 1. It is given us the question that PB is a tangent to this circle point B. So PB is a tangent, it is absolutely a straight line. So if you focus on the upper side of this straight line PB at point C, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles from one side of the straight line is equal to 180 degrees. So which angles we have at the upper side of PB at point C? We have this angle that is right angle plus this missing angle. In total, the sum of those two angles, they must be equal to 180 degrees. Therefore, this missing angle must be equal to 90 degrees inside. In the next step, we did the construction, that is to say, from this point O, we draw perpendicular on AC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. By doing this construction, we created quadrilateral OECB. Inside quadrilateral OECB, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total must be equal to 360 degrees according to the rule. It says that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees inside. So inside quadrilateral AECB, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be this right angle if not a square. So we relate to quadrilateral OECB is right angle because it has 4 right angles. But we also know that the opposite sides of a right angle are equal to each other. So a right angle OECB, side OE must be equal to the opposite side BC. But BC is 1, therefore OE must be also equal to 1 unit in its length. Likewise, according to the sum rule, in the same rectangle OECB, side OB must be equal to the opposite side OB must be equal to the opposite side EC. But OB is x, therefore EC must be also equal to x units in its length. What is the length of the missing 970 AE? From the drawing, it is very easy to see that AE equals to AC minus CC. Again, AE equals to AC minus CC. So AE equals to AC, that is 3, minus CC, that is x. So in total, AE equals to 3 minus x units in its length. In the next step, we join points O and A together by a straight line. OA is the radius of this circle that is equals to x according to our definition. In the next step, I copy the right hand triangle OAE in the new page and implemented the Pythagoras theorem on this right hand triangle OAE. This is the right hand triangle OAE that according to the original drawing, according to the Pythagoras theorem, in this right triangle OAE. OA squared, that is the square of the hypotenuse, is equal to AE squared plus OE squared. OA is x, therefore OA squared is x squared, which is equal to OE squared. OE is 1, therefore OE squared is 1 squared, that is 1, plus AE squared. A is 3 minus x, therefore AE squared is 3 minus x squared. So in total we found out that x squared equals to 1 plus 3 minus x squared. So here we have x squared equals to 1 plus 3 minus x squared. So, and 3 minus x squared equals to 3 squared, that is 9, plus x squared, minus 2 times 3 times x, that is minus 6x. So in total we found out that x squared equals to 1 plus 9 plus x squared minus 6x. Here we have x squared on both sides of the equation. So x squared will get cancelled. After we cancel x squared, on this side of the equation we left with nothing, that is to say 0. On the other side of the equation we have 1 plus 9, that is 10, minus 6x. So in total we found out that 0 equals to 10 minus 6x. Here we added 6x to this equation, and finally found out that 6x equals to 10. Here we divided this equation by 2, and finally found out that 6x over 2 is 3x, and 10 over 2 is 5. So in total we finally found out that 3x equals to 5. Here we divided this equation by 3, and finally found out that x equals to 5 over 3, and it's 9. So we found out that the radius of this circle x is equals to 5 over 3, and it's 10. Our mission is to find out the area of this circle. The area of any circle is equal to pi times the radius of the circle squared. Okay, then the area of any circle is equal to pi times the radius of the circle squared. So the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle is x. Therefore the radius squared is x squared. So in total the area of our circle must be equal to pi x squared. X is 5 over 3, therefore x squared is 5 over 3 squared. Therefore in total the area of our circle must be equal to pi times 5 over 3 squared. 5 over 3 squared is 5 squared, that is 25, over 3 squared, that is 9. So in total we actually found out that the area of the circle is equal to either 25 pi over 9 square units, so in terms of numbers the area of the circle is equal to 8.727 square units. We finish with the first question. In the next step I continue to read the second question and we solve it. Our mission in the second question is to find out the area of this trapezoid ABCD. It is given as the question that AB equals to 16, AD equals to 17, BC equals to 25, and DC equals to 44. The area of any trapezoid is equal to the sum of its two parallel bases times the height over 2. So the area of our trapezoid ABCD must be equal to the sum of its two parallel bases. The two parallel bases is AB and DC. Therefore the sum of the two parallel bases is AB plus DC times the height h over 2. And again, the area of our trapezoid ABCD is equal to the sum of its two parallel bases, that is actually AB plus DC times the height h over 2. The height h must create 90 degrees with the two parallel bases AB and DC. So in total the area of trapezoid ABCD equals to AB plus DC times h over 2. In order to find out the area of trapezoid ABCD, we did a construction. That is to say, from this point A, we draw perpendicular on DC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the length of line 70 is x, and the length of line 70 is h. H that equals to AE is the height of trapezoid ABCD. Why h is the height? Because the h creates 90 degrees with the base DC. Therefore h is also the height of trapezoid ABCD. In the next step I copy the right triangle AED in the new page, and we implement the Pythagoras theorem on this right triangle AED. Okay. This is the right triangle AED that I got from the original domain. According to the Pythagoras theorem, in this right triangle AED, AD squared, that is the square of the hypotenuse, is equal to AE squared plus DE squared. AD is 17, therefore AD squared is 17 squared, that is 289, plus AE squared. AE is h, therefore E squared is h squared, plus d square. D is x, therefore d square is x square. So in total, actually, according to equation 1, we found out that h square plus x square equals to 289. Again, h square plus x square is equal to 289. This is according to equation 1. In the next step, we did another construction. That is to say, from this point B, we draw perpendicular on DC. Okay, from point B, we draw perpendicular on DC. So this angle equals to 90 degrees, and this angle is also equal to 90 degrees according to our construction. We define the touching point of the perpendicular from point B and DC. This point is point F. So here we have, here we can implement rule 16. Why? Because we have those two angles. They are both located between the parallel lines AB and DC, and therefore they are defined as interangles. In addition, those two angles they are both located on the right side of the straight line AE, and therefore they are also defined as one-sided angles. So in total, those two angles they are both defined as one-sided interangles. And according to rule 16, the sum of two one-sided interangles is equal to 180 degrees. So if we look at rule 16, according to rule 16, the sum of one-sided interangles is equal to 180 degrees. Those two angles 4 and 5 they are both defined as one-sided interangles, and therefore according to this rule 16, the sum of those two angles is equal to 180 degrees. Here, angle 4 plus angle 5 is equal to 180 degrees. Likewise, those two angles are both defined as one-sided interangles, and therefore the sum of them is equal to 180 degrees. That is to say, angle 3 plus angle 6 is equal to 180 degrees according to this rule, rule 16. So we can actually implement rule 16 in our drawing. Right, because in our drawing we have those two angles. They are both defined as one-sided interangles, and therefore the sum of them is equal to 180 degrees according to rule 16. So this angle is a right angle according to our construction, and this is the missing angle BAE. So in total, the missing angle BAE plus this angle, that is the right angle. In total, the sum of those two angles, they must be equal to 180 degrees according to rule 16. So repeat again, according to rule 16, the right angle, the angle that is equal to 90 degrees in size plus the missing angle BAE plus the missing angle BAE, in total they must be equal to 180 degrees because of the fact that those two angles are both defined as one-sided interangles. Here we subtracted 90 degrees from this equation and finally found out that the missing angle BAE equals to 180 degrees minus 90 degrees, that is 90 degrees. So actually, this is the missing angle BAE, according to rule 16. The missing angle BAE is equal to 90 degrees in its size. Likewise, those two angles they are both located between the parallel lines AB and DC, and therefore they are both defined as interangles, and those two angles are both defined. They are both located on the left side of the straight line BF, and therefore they are also defined as one-sided angles. So in total, those two angles they are both defined as one-sided interangles, and therefore according to rule 16, the sum of those two angles is equal to 180 degrees. So this is the right angle plus this missing angle, that is angle ABF, is equal to in total 280 degrees. Repeat again, according to rule 16, the right angle, the missing angle ABF plus the right angle, in total the sum of those two angles they must be equal to 180 degrees because both those two angles are defined as one-sided interangles, and according to rule 16, the sum of two one-sided interangles is equal to 180 degrees. So here we subtracted 90 degrees from the equation and finally found out that the missing angle ABF is equal to 180 degrees minus 90 degrees is 90 degrees. So actually, this is, let me see that again, ABF, that's equals to 90 degrees in size. So actually, in total, we should find out that inside quadrilateral ABFE, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be this rectangle if not a square. So we relate to quadrilateral ABFE is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ABFE, side AB must be equal to the opposite side FE. But AB is 16, therefore FE must be also equal to 16 units in its length. Likewise, according to the same rule, in the same rectangle ABFE, side AE must be equal to the opposite side BF, but AE is edge, therefore BF must be also equal to edge. What is the length of line segment FC? From the drawing, it is very easy to see that FC in total equals to DC minus DE minus DF. Again, FC in total equals to DC minus DA. Again, FC in total is equal to DC minus DE minus DF. So FC equals to DC, that is 44, minus DE, that is X, minus EF, that is 16. So in total, FC equals to 44 minus X minus 16. 44 minus 16 is 28. So in total, this expression equals to 28 minus X. So in total, we should find out that FC equals to 28 minus X units in its length. In the next step, I copied the right triangle BFC in a new page and we implemented the Pythagoras theorem in this right triangle BFC. Actually, this is the right triangle BFC that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle BFC, BC squared, that is the square of the hypotenuse, is equal to BF squared plus FC squared. BC is 25, therefore BC squared is 25 squared, that is 625, and it is equal to BF squared. BF is just, BF is 8, therefore BF squared is 8 squared, plus FC squared. FC is 28 minus X, therefore FC squared is 28 minus X squared. So in total, if we found out that according to equation 2, 625 equals to 8 squared plus 28 minus X squared. Here we subtracted 625 from this equation, but actually, before we subtract 625 from this equation, we have to open the brackets on this expression, 28 minus X squared. And after we open the brackets on this expression, 28 minus X squared, we get that 28 minus X squared equals to 28 squared, that is 874, plus X squared minus 2 times 28 minus X, that is minus 56X. So in total, if we found out that this is 625, that 625 equals to 8 squared plus 784 plus X squared minus 56X. And after we subtract 625 from this equation, we get that in this side of the equation we left with 0, on the other side of the equation we have 874 minus 625 is 159. And if we add 56x to this equation, we get that 56x equals to 8 squared plus X squared plus 159. According to equation 1, 8 squared plus X squared is equals to 289. Therefore, we can substitute 8 squared plus X squared in this equation by 289. We did it, and we found out that according to this equation 2, 56x equals to 289 plus 159. So 56x equals to 289 plus 159 is 448. So in total, we found out that according to this equation 2, 56x equals to 448. Here we divided this equation 2 by 56 and finally found out that x equals to 448 over 56 is 8. So x equals to 8 units in its length. According to equation 2, we already found out that x squared plus x squared equals to 489. But x is 8. If x is 8, it means that x squared is 8 squared, that is 64. Therefore, we can substitute x squared in this equation 1 by 64. We did it, and we found out that x squared plus x squared, that is 64, is equal to 289. Here we subtract 64 from this equation and find out that h squared equals to 289 minus 64 is 225. So h squared equals to 225. We took out. Here we took out of this equation 1 and finally found out that h equals to the square root of 225, that is 15. So we found out that the height h of trapezoid ABCD is equal to 15 units in its length. Our mission is to find out the area of this trapezoid ABCD. I already explained to you that the area of trapezoid ABCD is equal to the sum of its two parallel bases, that is actually B plus DC, times the height, that is h over 2. So AB is 16, DC is 44, the height h is 15 divided by 2. 16 plus 44 is 60, h is 15 divided by 2. 60 over 2 is 30, so in total this expression is equal to 30 times 15, that is 450. In total, if we found out that the area of this trapezoid ABCD is equal to 450 square units. Then again, the area of this trapezoid ABCD is equal to 450 square units. Okay, thank you very much.